In this section, we will work with quadratic functions in real-world situations. Let's consider solving real-world situations that involve quadratic functions. Consider an object being launched into the air. We compare the height versus time elapsed. So here we have our graph of an object that was launched. We're keeping track of how long it's been in the air and its height from the ground. From what height is the object launched? So launching would be at the very beginning of the problem. So right here, the circle, it represents the height the object was launched. So at 0 seconds, it was at 3 feet. Meters. 3 meters. Once the object is launched, how long does it take to reach its maximum height? So as we're following along the curve, we get up to this point and then it turns and starts to go down. So the maximum height is right here where this box is. That would be called the vertex. So the maximum height is going to occur at the vertex. And if we follow the dashed line down, we're looking at about 2.5 seconds. What is the maximum height? So we'll still be looking at the vertex, but now instead of looking at the time, we want to know what is the height. So we'll go to the y-axis. And it looks like it's about 5 meters. Once the object is launched, how long does it take it to hit the ground? So if we're going to hit the ground, that means the height equals 0. So the object is launched, comes back down, hits the ground right here. So that would be the star. And it looks like it's about 6 seconds. Maybe closer to 6.5 seconds. Once the object is launched, when does it return to the height of 3 meters? So we'll use a straight line for that. So it started at 3 meters. We'll follow 3 meters all the way across. Right here, it's returning to 3 meters, which occurs at 5 seconds. So we just kind of estimated and read things off the graph. Let's look at mathematically how we could find these things. So if they're asking you what height was it launched from, that means you're looking for the y-intercept. So if you're looking at your equation in standard form, ax squared plus bx plus c is your y-intercept. So you'd be looking for 0c. Your y-intercept would be the starting height. It's where it's launched from. How long does it take the object to reach its maximum height? So maximum height is going to occur at your vertex. And if we're looking for how long, that means we're looking for time. And time is x. So we need the x coordinate of the vertex. To find this, you have to do the opposite of b divided by 2a. This is also your axis of symmetry. If they want to know what the maximum height is, so now you need the y value instead of the x value. So you're going to want the y coordinate of the vertex. You're going to substitute the x coordinate that you found in the step above, plug that into your equation to find y. So plug opposite of b over 2a in for x to find y. How long does it take the object to hit the ground? So if you're bringing something all the way back down to the ground, that means your height is going to be 0. So you have to set your equation equal to 0. So you're solving, you're going to be looking for the x-intercepts or the solutions or the zeros of a quadratic function. So you have many ways of solving. You could factor, you could use the quadratic formula, you could complete a square, but what you're looking for is the x-intercept. So I would recommend that you use the quadratic formula, which is x equals the opposite of b plus or minus the square root of b squared minus 4ac. This is your discriminant, all divided by 2a. So if you want to know when you're taking something all the way down to the ground, you set it equal to 0 and you solve with the quadratic formula. When does the object return to a height of, in this case, 3 meters? So if you have your function, if height is given, then substitute the value for height and solve. If they give you a time, substitute that in for time and then figure out height. So let's give this a shot. Ferdinand is playing golf. He hits a shot off the tee box that has a height modeled by the function h of t equals negative 16t squared plus 80t, where h of t is height in feet and t is the time in seconds that the ball has been in the air. The graph that models the golf ball's height over time is shown. So you can see that the ball starts here, which appears to be on the ground. It goes up, hits a maximum height, comes back down, and hits the ground. When does the ball reach its maximum height? So in our equation, h of t equals negative 16t squared plus 80t. Our a value is negative 16, and our b value is 80, and our c value is 0, because there's no constant on the end. If we're looking for maximum height, and we want to know when does it reach its maximum height, we're solving for time, so how long does it take it to get there? We need to come up with the axis of symmetry. So we're going to use the formula x equals the opposite of b over 2a. So we plug all of our numbers in. The opposite of b over 2 times a. And then in a calculator, we can put in 2 times negative 16 to get our denominator cleaned up, negative 32. So we're talking about negative 80 over negative 32. And we get 2.5. So when does the ball reach its maximum height? 2.5 seconds. Which, if we look at our graph, its maximum height would occur right there. Seems to be pretty darn close to 2.5 seconds. What is the maximum height? So according to our paper, if we need to find the maximum height, we have to plug the opposite of b over 2a, so our axis of symmetry, in for x to find y. So we're going to plug our 2.5 in for our t value. So I guess this probably should have said t equals. So h of 2.5 equals negative 16 times 2.5 to the second power plus 80 times 2.5. Punch all that into your calculator, and you end up with 100. So we're talking about 100 feet. So it takes 2.5 seconds to reach the maximum height, which is 100 feet. What is the height of the ball at 3 seconds? So if we take a sneak peek at our graph and we go up at 3 seconds, we're going to be right here. It's in between 90 and 100, but we're not 100% sure where that is. So they want to know what is the height, and they're giving us a time. So that means we can plug 3 in for time. So h of 3 equals negative 16 times 3 squared plus 80 times 3. Plug all that into the calculator, and you get out 96. So in 3 seconds, the ball is at 96 feet, which seems to fit with our graph because we said it was going to be in between 90 and 100. When is the ball at the same height? So if we look at our graph, we take our 96 feet across the other side of the graph. It looks like we're at 2 seconds. So ball is at 96 feet again at 2 seconds. So it hits the 96 feet on the way up and on the way down. When is the ball 65 feet in the air? Explain. This time they're giving us a height. So we're going to have to plug the 65 feet in for height and solve for time. So 65 equals negative 16t squared plus 80t. Because this is a quadratic, we're not going to be able to solve by undoing the order of operations. So we need to get it set equal to 0. So move the 65 to the other side. And then we're going to have to solve with the quadratic formula. So a is negative 16, b is 80, c is negative 65, and we'll plug everything into the quadratic formula. So as the opposite of b, plus or minus the square root of the discriminant, which is b squared, minus 4 times a times c, all divided by 2 times a. So if we do a little bit of simplifying, we grab our calculator and do 80 squared minus 4 times negative 16 times negative 65. So if we type that in, we have 80 squared minus 4 times negative 16 times negative 65. And we get 2,240 all divided by negative 32. So we're going to get one answer from our addition work, and we're going to get one answer from our subtraction work. So we do negative 80 plus the square root of 2,240. So there's the numerator. Divide by negative 32. We get 1.021. And when we do our subtraction work, negative 80 minus the square root of 2,240 divided by negative 32, 3.979. So at 1.021 seconds and 3.979 seconds, the ball is at 65 feet. So if we go look at our graph, find 65 feet, touches just after 1 second. And again, looks like it's just before it gets to 4 seconds. How long will it take the ball to get to the ground? So hit the ground, that means height has to be 0. So now we're solving 0 equals negative 16t squared plus 80t. You can use the quadratic formula for this. A would be negative 16 and b would be 80. But I'm going to solve this one by factoring. So I recognize I do not have a c value. So both terms have a t in them. So I can pull out a GCF of t. And let's see, I believe that 16 will go into 80. 5 times. So 80 divided by 16 is 5. So I can pull out negative 16t. So if I divide this by negative 16t, I'll just get t. If I divide this by negative 16t, I'll get negative 5. So I have 0 equals negative 16t times the quantity of t minus 5. Then I'll use the zero product property. Something times something equals 0. So I can set them each equal to 0 and solve them to find my x-intercepts or my zeros. So this one, divide both sides by negative 16. T is 0. So at time 0, the ball is on the ground, which is supported by our graph. This one, I'll add 5 to both sides. So t is 5. So that means the ball will hit the ground at 5 seconds. So it's starting on the ground at 0, and it takes 5 seconds to come back to the ground. So it takes 5 seconds until the ball hits the ground. Okay, our last set of questions. A neighborhood threw a fireworks celebration for the 4th of July. A bottle rocket was launched upward from the ground with an initial velocity of 160 feet per second. The formula for vertical motion of an object is h of t equals 0.5 a t squared plus vt plus s, where the gravitational constant a is negative 32 feet per second. Feet per square second. V is the initial velocity. S is the initial height, and h of t is the height in feet modeled as a function of time. So we have a function rule, but it's not all filled in for us. It says A is 32 feet per second per square second. So we have a number for A. V is the velocity. S is the initial height. H of t is height at any given time. And then we go back to the actual story problem. A bottle rocket was launched upward from the ground. So it starts on the ground. So S equals 0. With an initial velocity of 160 feet per second. So that's V. V equals 160. So I think we have enough information to fill in. So we have h of t equals 0.5 times a is negative 32 t squared plus velocity is 160. And then our starting height was 0, so technically plus 0. And we can simplify this a little bit. We can do 0.5 times negative 32, which is negative 16 t squared plus 160 t. That would be our equation to describe the height of the bottle rocket at any given time. What was the maximum height of the bottle rocket? So they want us to find the y value of the vertex. So you'll have to start by finding the x value of the vertex, which is the axis of symmetry. So we need x equals the opposite of b over 2a. A is negative 16, b is 160, c is 0. So plug our numbers in. The opposite of b divided by 2 times a. Negative 160 divided by negative 32 is 5. So in 5 seconds, the bottle rocket will reach its maximum height. Now we need to plug this time in to our equation to find that height. So h of 5 equals negative 16 times 5 squared plus 160 times 5. And we put that in a calculator. Negative 16 times 5 squared plus 160 times 5. We get 400. So 400 feet. So the maximum height is 400 feet, and it occurs at 5 seconds. So make sure you refer back to your chart on page 148 so that you know what things you can do to help answer these questions.